Hi, everyone. Good morning. My name is Ghida. I'm a lead quantitative engineer at Meta, part of the infrastructure org. And today I'm going to talk about AIOps, or how to enable AI and ML-driven operation for highly distributed IT infra. Okay, sorry, I think. Yeah. So disclaimer, this talk is not Meta-related. It's a personal opportunity. Of course, it draws on my experience for the past 5 years at Meta, but also in other places, my PhD work, my research, my knowledge of the industry. So I'm not representing Meta here, just to make it clear. Okay. The agenda, I will start by describing what a distributed IT infra looks like, although I'm sure that you are familiar with it in this audience. I will clarify a bit the similarities and the differences between AIOps, MLOps, DevOps, because there are overlaps, but there are also differences. I will talk about few use cases where we are using AI and ML to automate IT operations at scale. For instance, how do we use AI and ML to do capacity scaling, to decide on capacity placement, to do workload orchestration, to create correlation and causation between quality of service and quality of experience, and finally to generate alarms or simple alarms and do root causing. And at the end, I will leave some time for questions. Okay, so what does a distributed IT infra looks like? So high level, you can think of it as a distributed clusters of servers connected to each other and to the internet, and on top of which you have many apps and services running. And as you can see, many services can run on the same cluster, and this is a concept that we call multi-tenancy. So an example of such infra is a content delivery network. And you can think of a content delivery network as a network of edge clusters that ensure a reliable and fast delivery of static content, such as video, photos, and text to end users. So take the case of Liz, who is in the US, went on vacation, uploaded like a video on Reels on Instagram. And her video content will go through an edge server that is close to her all the way to an origin cluster. Her friends in the US would be able to fetch this content directly from the edge cluster, whereas her friends in other parts of the world would have to go in the first instance to the origin cluster. The content will be stored on the edge and then will be fetched on the edge for next request. So as you can see here, this can really distribute the load and ensure a low latency delivery of content. So how this happens, of course, you have the physical layers, the servers, the clusters, the connectivity, and all of these. But you have in the middle what we call the control plane, which is basically the intelligence layer supervising this data or physical plane. And this is where you have functions like capacity scaling and provisioning, load balancing, monitoring of capacity in real time going on. And these functions are very crucial, and it's really important to do them in a very reliable way. And this is where AI and ML could be really key here. Another example of distributed infra is cloud. So here you can see the availability zones and the region of AWS, which are available publicly. And in each of these zones, as well as in CloudFront zones, you would find a lot of physical infra, like computing instances, storage instances, both SQL, NoSQL database, etc. And on top of which, you have also a bunch of these control level layers, such as request routing through Amazon Routes 53, executing scaling through Amazon Scaler, and also CloudWatch, which allows doing monitoring in real time. So you can see that a lot of these functions are also supported in cloud solutions. But we also have other distributed types of IT infra. For instance, cellular or broadband networks, blockchain network, Internet of Things network, but also multi-clouds. And this is where relying on the cloud control on the control plane of one cloud is not enough, because once you start using a bunch of clouds or a hybrid cloud architecture, you would need an even more intelligent control plane to manage all these providers. Okay, now I'm going to talk a bit about the difference between AIOps, MLOps, AIOps, and DevOps. So AIOps versus MLOps. AIOps is really about using AI and ML to manage IT operations at scales. You can think of it as MLOps, but applied to IT operations. So in this sense, AIOps is a subset of MLOps. At the same time, AIOps allows deploying a ML model in production. So basically, you would need a level of intelligence to be able to distribute ML workloads, whether these are training workloads or serving or inference workloads in a given infra. And this is where AIOps is needed. Now, AIOps versus DevOps, there are many similarities. So like the main similarity would be really like the goal here is automate and abstract IT operations. But the way they operate is quite different. And I would say like you can go through this slide in details, but basically, in my opinion, the biggest difference here is that AIOps is more suited for managing operations between multiple clusters or involving multiple clusters and even multiple players, whereas DevOps is more suited for managing operations within a given cluster. Also, AIOps offers some level of sophistication by taking into account things like efficiencies, like quality of service, quality of experience that are not necessarily core to how DevOps currently operate. Okay, now let's go through some use cases where AR or ML or other quantitative techniques actually can be used to drive like operations and optimization for distributed IT infra. So let's start with capacity scaling with time series modeling. This really consists of predicting demand for different products or services across geographies and time. So think that you have like a given service, let's say a video streaming service. You have some SLAs related to the service. Like I want to reach people in Brazil. I want to reach like 2 million people. At peak time, I'm expecting to have like 100,000 concurrent requests. So this would be part of your SLAs. But your SLA usually comes from product team. Once the product goes live, maybe the real patterns are different. So this is why you need past demand patterns. And of course, you need some market context because as you know, some markets could be like saturated. Let's say the US or Europe, they are saturated because the internet penetration is quite large. Other markets still have like room to grow. So this kind of knowledge is also a bit of human knowledge that should be kind of injected into this capacity forecasting engine that will give you forecasts about what would be the demand for video, what would be the demand for voice over IP services, what would be the demand for ML capacity over different geographies and for different services over time. And really what should be the outcome of this is really like how much compute capacity do we need, whether this compute capacity is GPU or CPU, whether it's physical or virtual, how much storage do we need, and this also applies to different types of storage, and how much network do we need in order to be able to connect compute and storage as well as connect these capacities to the end users. So how do we do this? We can use time series modeling, and there are different ways to do it, and different models that are available out there. Some of them you need to code yourself. Some of them you can import some libraries, such as Prophet, for instance. But basically, like some things to take into account when you decide to choose a certain like time series model. You need to look at your demand and see how it evolves over time. Is it constant? Is it generally growing? Is it generally declining? Is there any correlation between present or past observation? Do you see any seasonalities or holiday effects? And then based on this, you can choose between models such as moving average or autocorrelation or a combination of both, or you can use libraries such as Prophet or others. So really it depends on the time series characteristic here. Let me give some examples. So the animation here were really like bad, but anyway. So imagine you have a video on demand provider that wants to stream like 20,000 movies to 10 million users in Brazil and peak streaming around 8 p.m. This should be translated into an average query per second. And then you need to have an idea about how many bits per second you would have at peak. So you need to make some assumptions there about the resolution that you're gonna provide in general. Also, you need to know how much like this translates in terms of storage and bytes. And this eventually would translate into streaming capacity, storage units, etc. Same thing if we're thinking about an e-commerce provider also in Brazil as the same geography that is trying to build an ads model that have high precision. So they're really optimizing for precision here. And they have like 2 million data points and the number of features. This would translate into storage, but also compute capacity translated into floating operations and floating operation per second. And you would translate this into GPU storage units. And then you would, once you do this, you need to calculate the network capacity required to connect all of these. Okay, Another use case that is really important is really optimizing capacity placement. So we saw that we have forecasted the demand. We have decided that, well, we need that much GPU or that much CPU for this service over this amount of time. Where do we place the CPU? For instance, in this like Brazil example that I've just given, you can decide and go and put all this like capacity in one place, or you can decide to distribute it around the country. Maybe you decide to put it in another country and maybe bundle it with Argentina or something like this. So how do you take this kind of decision? Because they are really important. There are many elements that you need to take into account, such as scalability and avoiding bottlenecks and making sure where you're putting capacity is a place that you can scale, where you can add capacity. You're not limited by a government or like not availability of enough resources or even the size of the building or something like that. So this is scalability. Reliability, planning against failures, making sure you're fault tolerant, you don't have a single point of failure. Cost, so how do you really make sure that you reduce your CapEx, you reduce your OpEx? Because in most cases, you need to connect also to these places. And if you're placing servers in faraway places, then the cost of this connectivity would be really expensive. You need to optimize for service SLOs, service level objectives, like meeting the quality of service and quality of experience requirements of your service. And of course, there are other things such as sustainability that you need to take into account sometimes. So all of this come into the picture. And there are multiple ways to do it. And based on my experience working on this problem for different companies, sometimes we would go into a ranking kind of system where you would say, okay, like I have all these metrics. I have like many metrics, and I want to assign different weights to this metric. I come up with an aggregate normalized score for each candidate place where I can like build something, or for each option I have. And then I rank these options with respect to each other, taking into account all the elements or all the metrics that I care about. So this is one option. Another option is the constraint optimization or operations research, where basically you formulate this as an optimization model that you're trying to solve with variables, which is, should I go for this option or not? So basically think of it as a binary variable. And what you're trying to do here is really maximize a given function. Let's say you want to maximize the fulfillment of your service level objectives. But at the same time, you're aware of the cost. You want to minimize your cost, or like you want to keep your cost below a given level. So this can actually be formulated as an optimization problem that can be solved. And the key here is really to abstract the physical level into cluster level, because solving it for every server would make the problem very complex to solve. So having this cluster level abstraction would actually make this problem a bit practical, mathematically speaking. So some examples here is deploying regional content delivery network clusters in large countries to improve reliability and be closer to users. So this is like an optimization choice. Same thing, building data centers in Nordic countries to reduce cooling costs and energy consumptions. Okay. Now we come to the third use case, which is linking QoS and QoE. QoS being quality of service, and QoE being quality of experience. So QoS is really about answering this question. Is the infra working well? Like if I have a set of servers, a set of clusters, are they doing well or not? So it's really about the infra. Quality of experience is really subjective. It's about how the user perceives the experience. Like, is this video service that I'm running on top of this infra, are people happy about it? Are people leaving? Are people staying? Are they engaging? Are they clicking on stuff? So it's really subjective, and it's service specific, and it measures customer satisfaction. But this is what we really care about. This is like where the revenue would come from. So you really need to find a way to link both things. For instance, if you take a service such as video, QoS metrics, the relevant QoS metrics would be network speed, or what we call throughput. The quality of experience metric would be more the buffering ratio, because the more you have buffering, the more people are likely to leave. Also, the resolution of the video. Other services like real-time communication would require or would be sensitive to network latency variance. And this will impact the rate at which people would drop a given call, as well as the call rating. For ML training, for instance, processing speed is key, and it could impact model accuracy and performance. So really, linking QoS and QoE is about finding how does a given quality of experience metric impact a given quality of experience metric, if at all. So you really need to find this combination. And then really using techniques such as ML inference and regression model to be able to establish thresholds below or beyond which quality of experience degrades. So for instance, let's say that beyond this below this network speed, users will start feeling degraded like video experience. Or beyond this given variance of like a call, people will start dropping actually. So really being able to perceive these thresholds and to calculate them. So this is an example, for instance, of how like a metric called mean time between rebuffering. So this is like the mean time between different buffers. Like basically, if you're watching a given video, it's the mean time you're expected to see the other buffer. And the lower is the mean time, the worse the experience is for you. So ideally, you want this mean time to be very spaced. Ideally, you want as a user to never experience buffering, right? So the higher basically the MTBR, the worse it is the higher the MTBR, the better it is for the user, and the lower it is, the worse it is for the end user. And here we see it compared to download speed. And you can see here that you have a kind of like logistic regression going on with this, this speed more or less is beyond which you start to actually see improvement and below which you start to see regressions. So really you can have regression models built around this to understand this relationship between QoS and QoE and be able to predict QoE based on one or more QoS metrics. Okay, how much time I still have? Okay. Now we come to workload orchestration, which is really very essential. So as we have seen, we have different services. We put them in the capacity forecasting engine that we explained first that give us like what are the compute needs, what are the storage needs, etc. Now orchestration fulfills different function. So first, it needs to aggregate all these, like workloads that we define. So for instance, let's say that we have a streaming service and we say, okay, like we need this amount of CPU, this type of CPU in particular for this geography. Suppose we have different services that have the same profile. Let's say different streaming providers in Brazil. We can basically aggregate them together based on the capacity type that they require, but also the market that they are addressing or the geolocation they are addressing. So this is what we mean by workload aggregation. And it actually creates a lot of efficiency in using the infra. And then once you have been able to like aggregate these different workloads, what you do is you need to assign them to given clusters based on like the cluster capacity, based also on the capacity type, the volume, and also the level of quality of service and quality of experience you're able to achieve from this cluster. And this is why you need a lot of data, historical data from this cluster to tell you what have been the past experience for a given service from this cluster and towards a given geography. And then once you have done this assignment, you input this into a real-time traffic targeting system, which would use this to redirect users in real time to given servers, and would also take into account some real-time signals about like the cluster's health. So let's say in theory, I'm supposed to redirect users to a given cluster, but this cluster fails suddenly, then I need to come up in real time with an alternative strategy. And here we explain a bit how AI and ML can play a role in this. So for aggregating different workloads, we can use clustering techniques that group workloads together based on similar capacity needs and geo-proximity. So you can say these workloads are most similar to each other. I'm gonna put them together because they have all these things in common, like capacity type, geography, etc. Right? Then on the part related to assigning workloads to specific clusters, you can here again use constraint optimization, where your goal really is to maximize the service level agreements fulfillment. So you want to serve as many users as possible with the right quality of experience, but at the same time, you want to account for the capacity limitations on your clusters. And finally, you direct customer requests to clusters based on workload assignment and real-time signals. And here you can also use like real-time optimization, such as reinforcement learning, to adapt your decisions in real time. Okay. I think I'm gonna end here because I think I've taken a lot of time. There are other use cases. I'm happy to speak about them like during the break or at lunch. I'll be here till lunch at least. So this is the conclusion. AI and quantitative techniques play a crucial role in helping scale and optimize large-scale IT infrastructure. There are a wide range of techniques, and even for the problems that I just presented, there might be other techniques that can apply. So you can go from simple analytics into time series modeling, into optimization, into regression, into inference, and other stuff. And there is always room for more. Thank you so much. If you're interested in discussing more about AIOps and how it can apply to your organization or to your problem, please feel free to reach out to me like during the break or at lunch, or to add me on LinkedIn and reach out. I'm always happy to discuss. Thank you.